So, hello everyone, and I hope the year has started well for you despite the fog and the cold and everything that Walla Walla seems to always have at this time of year. I've been there, I've seen it. So today's session that I'll be doing is going to be about pumps and water supplies and how to mirror those in Irricad. So when we're using water supplies with pumps, there's a few things that we need to consider. And one of those things is what type of water source we have. So is it a dam or pond or tank? Is it a well or a bore? Or is it a river? The other thing that we need to consider is the position and types of the pump. So if it is a surface pump, where is the pump position? Is it on top of the dam wall? Is it at the bottom, pumping out of the bottom of the dam or water tank? Is it pumping out of a well or a bore? Is it pumping out of the river? And if it's a submersible pump, what type of water source is it? Is it a dam, pond, or tank? Is it a well? Or is it pumping out of the river? Now, these things all come together to help us know what type of information we put into the water supply or the water source that is in our Irricad design. So they are measured differently depending on the pump type and position. So if it's a surface pump, the important thing is what is the level of water below or above the pump in meters or feet. And if it's a submersible pump, where is the water level relative to ground level? So depending on the pump and depending on the source, these will be different. And I've put a note there for myself. I mean, you probably know this off the top of your head, but one foot of head is 0.433 pounds per square inch. So I'll have to keep that in mind if I need to do any calculations. Right, so the time that we would be putting negative design heads into the water supply is if the surface pump is pumping out of a well, so the water level is below the pump, or if you have a submersible pump that where the water level is below ground level, so such as in a well or a dam where the water level is definitely below the normal ground level. The situations where we would be putting in a positive design head is if the water level is above ground level, such as an artesian well. So if it was uncapped and allowed to be static, it would be shooting up in the air or dribbling over the top. That would be a positive design head. And if the water level is above the pump, such as when you are pumping out of a dam from the bottom, or if you are pumping out of the, near the bottom of a water tank. And there are also situations where you would set the design head to 0 or close to 0. And that is where the design head is atmospheric. So that is situations like when you're pumping out of the river, particularly if it's a submersible pump in the river. If your surface pump is quite high up the bank from the water level in the river, then you would put in a negative design head again. But if the pump happened to be quite close to the natural level of the river, then you would put in 0 or close to 0. And there's also other factors to consider when you are using pumps in an Irricad design. So for surface pumps, you might want to add in the allowance for suction hose losses, Headworks losses, such as, what is in around the pump station, such as pipe work, elbows and tees. isolating valves, filters, etc., etc., etc. And if you're pumping out of a well, there will be drawdown in the well. So that's irrespective of whether it's a surface pump or a submersible pump, there will be drawdown if it's a well. If you're using a submersible pump, then we're going to have losses in the rising column, as well as other headworks losses. So these items can all be included in the design for Irricad to hydraulically calculate the friction losses based on flow. So we can add those items one by one along the main line after the water supply. So we have our water supply and we've determined what the design head will be based on the water type, the water source type and the pump and position of the pump. Next, I like to place the pump on the main line, because if this is a negative pressure, we're going to have negative pressure in the pipe until the pump adds pressure into the system. So if I put this next, then I know there's only going to be one pipe with negative pressure. And if I'm getting messages about there being more than one pipe with a negative pressure, then I know that I need to go and have a look to see where that is. And here you can see that I've placed drawdown losses, rising column losses because my pump is a submersible in this case, headworks losses, and you can do headworks losses in a couple of different ways. You can have it as a set value, and you might want to do that for things like an automatic backwash filter or even a manual filter, where you know that there's going to be a pressure loss or a maximum differential across the filter before it will be cleaned, and you want to allow for that maximum so that you know that even when it's just before being cleaned, that there will be enough pressure in the system to provide the valves with the pressure that they need. And you can also have these values based on flow. So when there's a higher flow, there's a higher head loss. When there's a lower flow, there's a lower head loss. You can also create pumps that only input the required pressure. So if you're designing a system and go, okay, well, at this point, I'm going to need 70 PSI, you can place a pump into the system that just does that. But if you're not actually going to put in a fixed flow pump at that place, once you've come to the end of the designing process and you know what you require, perhaps in multiple places, you should replace those fixed flow pumps with actual pump curves to check those system pressures over the different system duties. And not only can you put in main pumps near the water supply, you can also put in booster pumps anywhere in the design. Just place them on the main line. Just make sure they're not connected to any other point object, that they're just on the main line. And don't put them in loops or ring mains. So we're going to have a look at putting these different items into the database and doing a quick design. Now I need to change screens, so just bear with me while we do that. I'll minimize this. And we'll go to well, let's go to the database first. So if I bring that up. Right, can you see the database? Yes.
We can see that, Jo. Thanks.
Okay, so I've actually put the pump in, but I'll show you how I did it. I just need to move that out of the way. Right, so with pumps, you want to have a pump curve that you can get information from into the database editor. So here we have, oh, this is going to be awkward, isn't it? Oh no, it's a screen, not an application. That's cool. Can you see the manual on the screen?
No, we can't, Joe.
You're just seeing the database editor.
Yeah. You'll need to share the screen, not the application, I think.
Well, it does say screen sharing. So let me just see what I can do. Except it doesn't want to pop up. Ah, because I'm looking on the wrong screen. Sorry, my controls have gone very small and I can't seem to get them bigger. Okay, stop share. Let's go. Share screen. Okay, can you see the notes now?
Yes.
Okay, so when we're using a pump, we're going to have a look at a pump curve. And of course, if you have a table with the pump curve, that's a lot easier than reading the information off the screen. So here we can see that this particular pump curve has all sorts of different units. So you can choose the ones that you like to use. So we've got bar, we've got meters, cubic meters per hour, liters per second for metric, and we've got feet, US gallons per minute, and if you really want to, imperial gallons per minute. And when we go back to the database editor, hopefully that shows straight away.
Yep.
We can see that we can choose all sorts of different units for the flow and for the pressure. So you can choose whichever ones you want, as long as you make sure that you keep reading the correct units off the chart. So I'm just going to put in the metric ones because that's the ones that I'm used to reading off this chart. And we're just going to put in this 6-bar curve here. So when I enter the information, you need at least 3 sets of data to be able to get the curve fitting to produce some numbers for you. But put in as much as you can within the working area of well, in this case, a pump. Okay, so these are just figures that I have read off the graph. We click Fit Curve, and well, they're slightly different what I had there before. If you want to update the information, that's there. And you will do, when you put in a new item into the database editor, it's going to copy either the first item in the list or the a specific item that you've selected. If it's quite similar, then there's only a few things you need to change. But one of the things you will be changing is the hydraulic performance of the item. So just click the arrow, and here we can see a curve of best fit. And this R squared is just telling you how accurate things are. So if you've put in an incorrect number, it should pick it up. And if it's below 80%, then it will give you a warning. But by clicking this green arrow, it has now populated the relevant fields with the information that it needs. Make sure it says yes. And what I'm going to do for the purposes of this tutorial is just change the connection codes to pump so that we can easily see this in the reports that we're going to be looking at in a minute. Okay, so we've given it a plotting symbol. It has a price. It has minimum and maximum flows, and of course the hydraulic data that we've told it needs to have. So then Irricad knows how this pump is going to perform based on the flow going through it. Okay, so here is the item. Now, the other items that we need to consider that we can see in our little graph here are things like drawdown losses for a well or a bore. Now, drawdown losses are typically based on well tests. So this will be the pumping level minus the static water level. And the database group that we put it in is the other hydraulics. And this tends to have the equation of head loss equals a constant times the flow to the power of an index plus C, which is an intercept, which may or may not be used. And if we go back to the notes, we can see here that internally, regardless of what units you might put into the flow curve, the curve fitting table, internally, the head losses in meters and the flow is in cubic meters per hour. So if you were going to be working things out just using that equation, which is what I'm going to be doing because I only have one well test or one drawdown test, you need to make sure that it is in those units. Now, if you're not sure about these things, you can go to, sorry, I need to see this, help topics, technical reference, form of the equations, and it tells you the units that are used in these equations. So just make sure that you convert everything into the internal units before using these equations directly. If you have 3 drawdown tests, you can put them into the curve fitting utility for Irricad to calculate the constant in the index. So remember that the constant in the index is the way that Irricad explains the relationship. You know, how much pressure or loss in this case, how much pressure loss do you get based on the flow? If you have 2, you can use logs. I'm not very good at logs, so I wouldn't even attempt to do it. But for those of you that know how to do logs, you can definitely do that if you've got 2 readings. But if you've only got 1, you can just solve for this equation. Now, the drawdown or the head loss is equal to the actual distance that the static water level drops down to where the water level is under pumping. So the head loss in this case is 9.6 meters. And if I solve for that and find out what K is based on a known flow and an assumed index in this case, which I've given you some notes here, we're going to be using 1.5 as the index because the flow is less than 50 litres per second. But if it's uncased in rock or limestone, then you can use an index that's closer to 1. So these are just a rule of thumb that you can use if you don't have 3 drawdown loss well tests. So if we go back to the database, we can see here that the drawdown 9.6 meters at 49 cubic meters of flow. The assumed index is 1.5. if we solve the equation, we find that the constant is 0.0199243. So we would put that in. Is everyone familiar with how to solve these types of equations? And find the unknown constant in this case? Or shall I just quickly go through that?
Oh, I think we'll accept it. We'll accept what you've got there at the moment, Jo.
Yep, okay. So I've put this into the database. I've made sure it's got Y for usage, and I've just given it a dummy connection type so that I can easily see this item in the reports when we go and have a look at the effects of the pressure loss based on flow. Now, as we go back through, we can see that there's other things that need to be considered as well. And one of them is the rising column loss in the submersible pumps rising column, of course. Now, the index doesn't change based on length, but the constant does. So here we can see for our 6-inch pipe at 100 meters long, there is our constant and index. But we want to have one that is only, we have one that's only 65 meters long. So we need to solve for what the constant will be, which is a fairly easy calculation in this case, that we're just multiplying this number by 65 and dividing by 100. And that will give us this value here. And now note that anything that you put into the database, you should give quite specific description so you know exactly what they are, particularly in the case of drawdown losses. You probably want to put the client's name and well name in there if he's got more than one, so that you know it's specifically for that well. So here we've got, in this case, 65 meters of a 6-inch or 150 mil pipe. And once again, I've just given it an inlet connection code, an outlet connection code of RC for rising column, so that I can easily see this in the design reports when I go looking to see what the effect of the flow is on the pressure loss. Headworks losses. There's actually two ways that we can do headworks losses. One is to have it, as I explained before, that it changes based on the flow. And the other is that you have a set value. So if we say that we know that there's 3.5 meters of head loss at a flow of 100 cubic meters an hour, we can solve for the constant, and we find out that when we put that in, so missed losses 3.5 meters at 100 cube. If I've put in enough zeros, it will turn out all right. It's 0.00035 in this case. So that's on for selection. We've given it a special connection code. And the last one that we're going to be doing is the miscellaneous fixed loss. So I've only put 2 meters on this at the moment, but if you're going to be putting this in for to account for the pressure loss over a filter, then you might want to put that a little bit higher. But here you can see that there's no constant and there's no index. So this has no relationship with the flow. It's always and only going to have a 2 meter head loss every time this is placed in the system. Okay, so what we'll do now is we will place it on a design. So if we go first with our water supply, and this is going to have a value of minus 10, I think it is. Okay, so we have to untick calculate pressure when we are using pumps, -10. And the maximum head has to be equal to or greater than the design head. And I tend to just use the same value in 99% of cases. So don't calculate pressure, set the pressure based on the water supply or the water source type or the position of the pump as we discussed before. So place that. I'm going to put in a 8-inch pipe for the purposes of this particular tutorial. And then on that pipe, I'm going to place the other items. So let's go to pump. We're going to place that Pluga pump that we put into the database. Okay, so now I know that as soon as it gets past this point, there's going to be positive pressures in the pipe. And the other items are all in the MISC hydraulic component group. So we want to put in the drawdown losses and the rising column losses. Oops, MISC hydraulic. Miscellaneous losses. And of course, if you've got isolating valves and other things like that, then you can place those on the line as well. And MISC fixed loss. Okay, and on the other end of the pipe, I'm going to put an outlet. I'm just going to use a demand point for the purposes of this tutorial, which as you can see, you can follow along in the manual at a later date as well. And it is going to be pressure required 70 and flow at 100. So we'll place that on the end. Now this is what you would call a mainline design, that you don't have any zone pipe, but of course you need to analyze the zone, which is the outlet, so that the main line, the water source, knows what the outlet needs. So even though it's a mainline outlet, it's a valve and head outlet, and that is the zone. And we need to assign zones to system flow. So very simple on this one, just all zones to 1. So at that point in time, we'll be able to see what is happening in the system. And mainline design, I've already have a pipe size, so I just need to analyze that. And here's our negative pressure for just 1. And we're getting not enough pressure at our outlet. So if we have a look at that, this is object info. If you don't have it turned on, you can just tick this little checkbox here. And it is a bit under pressure. I think I must have put in some wrong numbers somewhere. Now we can actually query all of these items individually, but if we go to the mainline design full report, we'll be able to see very easily, because of my dummy codes, connection codes, what is happening here. So here we can see that at 100 cubic meters an hour, the pump is inputting 94.87 meters of pressure. The drawdown loss is 19.92 meters. Our rising column losses are 0.15. Our miscellaneous losses based on flow is 3.5, and our miscellaneous fixed losses is 2. Now, if we change the flow to 50 cubic meters an hour, come up, all right, 50 here. Now we've changed the zone essentially, so we just need to analyze that change and then reanalyze the main line. Okay, my pipe's a bit under pressure rated because of the lower flow. Let's have a look at that design report again. Here we can see instead of 94 meters of input, the pump is putting in 126 meters. Drawdown was it 28 meters before? It's now down to 7.04. Our rising column loss, which is 0.15, is down to 0.04. Our miscellaneous loss based on flow is down from 3.5 down to 0.88, and our fixed loss has not changed because regardless of the flow, it's going to give us that 2 meter head loss.
Joe, just a note of translation, when you had 100 cubic meters per hour there, that's about 440 gallons a minute. And she changed it to 50 cubic meters an hour, which is about 220.
Yes, I just halved the flow. So yeah, don't get too hung up on the units as the numbers that yep. Okay, so what we'll do now is we'll try and go back to the other screen.
The flow was changed and that changed the pump. Yes, the pressure rose significantly coming out of the pump. So changing the flow and change the horsepower. Well,
yes, at that lower flow, the pump inputted more pressure based on its pump curve.
The pump was fixed. Joe placed a certain pump in the design, and the initial design was at a higher flow. When she halved the flow, the pump came back on its curve and produced a lot more pressure. And that's pretty useful in this. You design for the worst case scenario a lot of the time with the highest flow, but to be able to see what happens when you're running at lower flow, it can really bump the pressure up in other places in the design.
Okay, so we'll just have a quick talk about the, whoops, sorry. Other things that might be in the, sorry, I keep clicking the wrong button. There we go. Okay, so you can put pressure reducing valves in a design. You can put them anywhere really, but if they're placed at the headworks, if they're going to be placed at the headworks, to do a quick design instead of putting in your pump and all your head loss items, you can just set the water supply pressure to what the PRV would be set to. And then you can quickly carry out the design and leave the pump sizing and headworks hydraulics to a later stage. And one thing to remember about PRVs as well as pumps is not to place them inside a loop or a ring main. When you're putting a PRV or brake pressure tank or wanting to put one in the design, you can use a miscellaneous hydraulic item that has PRV entered into the fitting field in the database. So, sorry, let's just see if I can drag that over. Can you see the database editor there?
Yeah.
And if we look at, here's a PRV, it has PRV in the fitting type. And as soon as Irricad sees that, when you place the item, it's going to ask you for what pressure you want downstream of the of that item. And as long as there's enough upstream pressure to deal with all the pressure loss through the item itself, then it will regulate. If it can't regulate, it will tell you that you don't have enough pressure to regulate. Other things like backflow preventers can be placed in Irricad for friction losses to be calculated, but just note that they don't actually stop the flow from going both ways in a ring main. Okay, it doesn't know, for backflow preventers or check valves that the flow can't go back the other way. So if it's in a loop, it will do so. And pressure sustaining valves don't actually ensure that the upstream pressure is sustained in an Irricad design. So once again, they're placed in the design for bill of materials purposes and for that friction loss calculation through the item. Multiple water supplies. Well, we've got lots of different design types. You can have one system with one water supply. And we can see here, you might not be able to see it there clearly, but the little water supply has gone sort of a maroony coloured because it's a combination of all these different colours of system flows. You can have one system with multiple water sources, and you may not see this clearly either, but these two water supplies are exactly the same colour because they are both supplying all of the zones in the system. You can also have multiple systems on the same design with their own water sources, and you can have one system with multiple supplies that supply separate valves. So just to make this easy to see, I've got a blue water supply supplying the blue zones, an orange one supplying the orange zones, red for red zones, teal for teal zones, and green for green zones. But of course, we can also have multiple systems with multiple water supplies on the same design. It all comes down to your management of the system flows. So system flows are, of course, a method that Irricad uses to specify which valves are running together. So at any one point in time, you want to look at it and say, well, what is running together at this point in time? Each system flow occupies a unique point in time. So if you have multiple water supplies supplying separate systems, they need to have unique system flows. So even if they're both running from 10 a.m. to 11 a.m., which is probably quite likely in the real world, you cannot put them into Irricad that way. The supplies need to have separate system flows. Now, if you've done it graphically or it's a bit hard to do graphically and you want to do it in the table, instead of putting in every system flow, you can use groups. So instead of going 1, 2, 3, 4, 5, 6, 7, 8, you can go -1 in the first column and -8 in the second column. And so you can see that this table shows that we've got supply number 1 supplying system flows 1 through to 8, supply number 2 system flows 1 through to 16. Oh, and I've made a bit of a mistake here. If they are all separate systems, I've got 16 in my supply number 3. If it is not connected to the valves that are running on system flow 16 and only supply number 2 is connected, when you run mainline design, it's going to say an item is not connected to the mainline. And if you run check outlet connectivity and it says, well, everything's connected, that's because check outlet connectivity checks to see that every outlet is connected to a valve if zones are present, and that every valve or mainline outlet is connected to a water supply. At that point, it cannot tell you that you've told a water supply to supply a valve that it's not physically connected to. So when you're getting those messages in mainline design, it's because you've done your management wrong. But you can also see here that we've got more than one group. So we've got system flow 16 through to 20, and also system flows 24 through to 28. And you can also put individual flows. So for example, it might be that supply number 3 also supplies system flow 41. So I would just put a positive 41 into one column. As soon as you use a negative number remember that it's part of a group and you need to have a negative number in the second or the next column as well. I just took a screenshot of this, of something I had existing. I've just realized it says 14 system flows and I've gone up to 40 already on the table. Right, fixed flows or fixed pressure. So these days in Irricad, you can tell a water supply to have a fixed flow and fill in the design flow and of course max flow as well of what that value should be. Now you can only do this if you have more than one water supply. Well, I guess you could do it if you have one water supply, but only if you have one system flow in the design. Because if you have multiple system flows and they have different demands, then you're going to be getting errors because, you know, the fixed flow is the fixed flow. And if it doesn't match what the demand is, it will tell you all about it. Okay, so you can set fixed flow on one or more water supply, but you need to have at least one where you have set the pressure. So these ones will be able to say, okay, this is the flow I need, and it will work out what the pressure will be at those water supplies. And then on the one or more that have a fixed pressure, it will work out the leftover flow, as it were, that it needs to have, that it needs to account for to make the system balance and work based on the other fixed parameters. Of course, you can have multiple water supplies and multiple pumps in a system. And if you're not going to be fixing the flow, which, well, it's been around for a few versions of Irricad, but previously you didn't have a choice, you would have to fix the pressures in all of the water supplies and make small changes until you had a balance of the amount of flow you wanted out of each water supply. And a small change in pressure could have a large effect on the flows. So if that's the way that things need to be because you don't know what flows you need out of each water supply, you can do it that way. It can be a little bit tricky if you have quite a tricky design or quite a lot of elevation changes. But if you add pumps into the system, it dampens it because those pumps can only work along the pump curve. And then the water supplies, of course, will be set to the value as we've discussed previously. So either the water level above ground level or the distance between the pump and the water level. So we can't add pumps in loops. So if we have the situation where we have physically one water supply and we've got two pumps in parallel that are feeding into a single main line, to get that to work in Irricad, you would need to just add another water source. So it looks like it's pumping from, you know, out of the pond or whatever it is, via two pipes through the individual pumps and then away into the main line. How are we going for time?
You're okay, Jo.
Cool. Okay, well, we'll do some exercises then and just have a look at these different things. So we will go back to the Irricad screen. And let's move you here. Okay, so you can see my Irricad screen.
Yes, yep.
Okay, so let's have a look at multiple water supplies on a system. So I'm just going to draw in a pipe, a particular length. And what I've done is a little bit two-step in standalone. I need to draw a straight line first, a particular length, and then I can convert it into the item that I want it to be. Of course, in length, you can specify the length of pipes as well as lines. Right, so we're going to have a water source over here. And they're going to be set to a particular pressure. And we'll do the same on this side. And we're going to place a demand point in the center, and that is going to have, yep, everything's 50 in this one. Okay, so we've got our outlet right smack in the middle between the two water sources, and in this simplistic view there is no elevation change. So I'm just going to analyze that mainline outlet, all systems to one system flow, and as soon as we've got more than one water supply, you will see the water supplies listed individually in the management. If you've only got one, you won't see it there. And let us analyze that. Okay, so if we look at the system duty now, sorry, I just need to change my reports folder. And look at our system duty. We can see that each water supply is supplying half of the flow, so it's evenly distributed. So there's no elevation difference between the position of the two water supplies, and the item that requires the flow is right in the middle. Now, as we move this item along and closer to one water supply and analyze that change. So we haven't actually changed the outlet itself, so we don't need to reanalyze the zone. Unless, of course, there is elevation, then you would need to reanalyze it so that the correct elevation is assigned to the item. I'm just analyzing the main line, and we'll go and look at that report again. Sorry, system duty. And here we can see that the water supply that is closest to the outlet is supplying most of the flow, and the water supply that's furthest away is supplying less of the flow. Now we can set these water supplies. If we say that this one is a fixed flow, and we're going to say, well, you need to supply 35 of the 50. This one, of course, is a fixed pressure, so you have to have one that's fixed pressure. You can't fix the flow or calculate the pressure. If we then reanalyze and look at our system duty report, we'll see that it is supply number 2 that is supplying the 35 out of the 50. And the closest water supply has found that the difference required is 14.97. And based on the pressure This water supply has calculated that it needs to supply 50.02 meters of pressure to get the 50 meters at the outlet. So this one was fixed, this one was fixed or fairly fixed. This was calculated, and the pressure was calculated on the other water supply. Any questions?
Looking good, Joe. How much longer have you got? We've got time, but just how much longer have you got?
Well, I was going to say I'm finished, but if we need to fill in some time, we could look at the pumps in series and pumps in parallel as a redesign too.
Are most everything that he's covering covered already as well as the help?
Question, Joe. What you've covered today, is most of that in the help files?
Yes, it is. So it is available in two places. The theory is available in the user manual, advanced topics, using a pump and a design, and there's the multiple water supplies there as well. And it is also available in the tutorial section, tips for advanced users using a pump and a design. And this has the same information in that I've been using in the little designs that I've been doing. Multiple water supplies, pumps in parallel and pumps in series. So you can actually work through it the way that I've done it and input that information. And yes, it does have US units in the tutorial as well.